we're going to talk about squaring a very large, tall, and skinny matrix. And we're going to do it in a distributed computing setting. I'm Reza Zadeh. This is joint work with Gunnar Carlson in the math department at Stanford and Ashish Goel in the management science and engineering department, also at Stanford, and I'm in ICME. So we have a tall and skinny matrix A, m by n. M is much larger than n. It's large enough that you want to be using, say, 100 machines to store, and you don't have the option of streaming this thing through a single machine. Now, so m could be as large as 1 trillion, and n will have two settings for it. It can be, for one setting, around 10,000, and for another task it can be around 1 million. I'll tell you what those two tasks are in a second. A is sparse. You know, matrices this large, they have to be sparse, or else it's pretty hopeless. So A has L non-zero entries per row. So it's row sparse. The columns can be as dense as you like, okay? But the rows, they must have some constraint. So we're computing A transpose A. That's what I mean by squaring this matrix. A transpose A is n by n. Remember, n is the smaller dimension. So A transpose A is considerably smaller than A itself, but it's dense, and it trivially holds all the dot products between columns of A. So that's what we're trying to find. We're trying to find all pairs of dot products between columns of A. Okay? And we'll do that with two guarantees. The whole setup has one knob gamma, and with the lower setting of gamma, you pay a lower cost, and in return for it, you get the highly similar pairs of columns computed accurately. So this is going to be an estimation of the pairwise dot products. And for those dot products where the columns are very similar, and similar I mean in terms of cosine similarity and some other similarity measures, these pairs are accurate estimately with a very low setting for gamma. And then if you're actually interested in singular values of A transpose A, you can then pay a little more and have those estimated accurately as well. So we're going to prove results for matrices in the first setting where their cosine similarity for the pairs that you're interested in are greater than S. So say you're interested in all pairs of columns that are more than 10% similar, you set S to 10%, 0.1, and then in this case, and in this talk, we're going to talk about cosine similarity, which is simply the normalized dot product. However, this will generalize to a lot of other similarity measures that I'll list in a table at the end. And for some notation-wise, Ci is simply the ith column, Cj is simply the jth column, etc. So nothing fancy here. And as a running example, you can think of the Netflix matrix. So the Netflix matrix has a lot of rows and fewer columns. There aren't that many movies in the world. There are way more users in the world. And it turns out that one other property of the Netflix matrix will be very useful to illuminate the properties of what I'm showing you, in that there are some rows that are very dense, i.e. there are some movies that have been seen by a lot of people. And there's a power law distribution on the column magnitudes, because there are some movies that are very popular, and then they tail off. All right, so we've already said that we're going to have a lot of machines involved, and there are a lot of distributed computing environments that take care of distributing your computation for you. MapReduce is one of the most popular. Nowadays, there are others. Scalding will take some Scala code and turn it into MapReduce jobs for you. Spark will take Scala code and directly do the distribution for you. There's code for what I'm telling you in both Spark and Scalding on my website, but not MapReduce, even though the entire algorithm is described in terms of maps and reduces. It just so happens that that's a nice way to explain it. That's not the implementation that's available on my website, because MapReduce itself is sort of not being developed so much these days. Okay, so we'll talk about maps and reduces and analyze that. So let's do the naive implementation of this, okay? You go into any simple interview that expects you to know MapReduce, and they ask you to compute A transpose A, this is what you would do. Okay, there's nothing fancy going on here at all. The rows of the matrix are being given to the mappers. So the rows are sparse. So it's very natural for the matrix to have been chopped up row by row. Because then you have this natural boundary where you don't expect for data to overflow because you have the constraint of sparsity on every row. So a mapper gets a bunch of rows, and in this case it's getting one row right now. And then it goes through all the non-zero pairs in that row and outputs the columns with which those pairs are associated and their multiplication. And the reducers will get all of that. So this is one little multiplication in a dot product. So dot product is the summation of a bunch of little multiplications. This is one of those little multiplications. The reducer just does the summation. Nothing fancy at all. Now we'll analyze this thing, okay? So there are two things to analyze in any MapReduce situation. First of all, you have to analyze the cost of communication between machines. And in MapReduce world, that's made rigorous by looking at the shuffle size, which is the total amount of stuff, the total number of key value pairs that the mappers output. So in this case, what is that? Well, it's going to be O of ml squared. Why? Because we're going to run this mapper over all of the rows of the matrix, of which there are m. And we're looking at all pairs of non-zeros in the row, of which there are at most L, and emitting. So L choose 2 is O over n squared, and that's it. So that's O of ml squared. So already there's a dependence on the very large dimension, m. So we're going to shuffle potentially all of the data around the network times L squared. And the largest reduce key is also of importance here, because not only do you have to analyze communication costs, you also have to analyze how much a single machine has to do, the actual computation costs. And that's encapsulated by the time that the longest reducer takes, because that's when your job finishes. Your job finishes when the very last reducer does. And that's going to take, in the worst case, O of m time. Because this summation here, there might be two columns that are identical, and they're going to have a very high overlap. For example, one column might be The Godfather, the other column might be The Godfather 2. There'll be a high overlap between those people. Most people have seen both those movies, and then that machine will get overloaded with people who watched The Godfather, or two vectors that are very similar. Okay? So in both those cases, there's a dependence on m, which is not really feasible for the scale that we're talking about. Now, we'll bring both of these down with some sampling, with the one assumption is that the column norms are known. So we're assuming that somehow we beforehand computed the norms of every column. There aren't that many columns. Remember, the number of columns is the skinny part. However, this will require a pass over the matrix. Right? Very often, you would have these computed beforehand. So if you're in a production environment, I'll explain some places where this is actually used in production. They already have the column norms computed. But apart from that, apart from computing the column norms, the rest of the computation is actually going to end up being independent of m. Okay? So that's why the whole thing is called dimension-independent matrix square, because apart from a part that you might have computed already, the rest of the computation is independent of the larger dimension. Okay? And the acronym is dimension-independent matrix square using MapReduce. So that's dim sum. I apologize for that, but at least you remember what this is about now. So let's modify this. Okay? So this was the original. Now we're going to do some clever sampling. Okay? It's going to be very similar to this original, but there will be some sampling. And if there's one thing, if you take one thing away from this talk, take away this slide. Okay? So we have the same setup. We have mappers and reducers. The mappers are getting rows. And again, we're going through all pairs of non-zeros in the rows. Now, instead of just emitting every time, we flip a coin with this probability. Okay? Don't turn off with this probability. Let me actually explain it to you. Okay? So this guy here, this is the important part. 1 over the magnitudes of the columns. This is pretty much everything. Like, just remember that the probability is inversely proportional to the magnitude of the column. So the more popular the columns are that are involved in this multiplication, the lower the probability of emission. Okay? So that might be unintuitive at first, because you're saying the more important the column is, i.e. the more people have watched this movie, the lower the probability of emission. But that's actually what we're doing. So the minimum here is just to make sure that this is a probability. That's why it's 1. And then the gamma is to satisfy concentration inequalities. Okay, so this is the important part, the inverse proportional to the column magnitude sampling. And the reducer is actually identical to before, except it undoes the fact that we're flipping some coins. So the output of the reducer is now a cosine similarity. Instead of being the dot product, it's the cosine similarity. So the BIJs, these are estimators for the cosine similarity, and this if condition is only there because of this min 1 condition. It's only checking to see if the probability of emission was 1 or greater than 1. And if it is, then it's in the first case, i.e. there was no sampling, and we simply, this is exactly the naive case. So we simply normalize by the column magnitudes and get back a cosine similarity. And if there was sampling, which is this case, then we normalize by gamma, because that's the only thing that stops this from, in expectation, being the cosine similarity between column I and j. So BIJs are the estimators for cosine similarities, and then we have to see how they concentrate. Any questions so far? If this is like I said, this is the slide that I want everyone to take away. So let's analyze this thing. The shuffle size for this will now be independent of small m. There won't be a dependence on m anymore. Instead, there was a dependence on n, l, and gamma. And we'll see that to concentrate, gamma doesn't need to be too large. The largest reduced key will only have a dependence on gamma, and again, there won't be a dependence. And the I promised two things with regard to the concentration. Similar columns are estimated when you set gamma to be log n over s. So s is the smallest similarity that you're trying to estimate. So if you're just trying to find the most similar movies and that are 10% cosine similar, you set s to 0.1 and then log n to log 10,000 or whatever the number of movies there are. And if you're looking to preserve the singular values within epsilon relative error, you would set gamma to at least n over epsilon squared. Okay, and these are 4 things to prove. This one is non-trivial, but it's pretty easy. This one is trivial. This one is, it's okay. I mean, it's Chernoff bounds. Most of you will just do that in an hour or less, maybe in your sleep. And this one required work. So this requires some matrix concentration inequality that's not very popular. Okay, so the proofs I can't go into right now. We don't have time, but everything's available in the papers. So there are 2 papers that I'm mushing together in this talk. There's a dimension-independent similarity computation, and then dimension-independent matrix square, and both of those are on my website. So the fact that neither the shuffle size nor the largest reduced key depends on m is because we're taking those columns that are appearing very often and penalizing them. So this should make you suspicious that things might not concentrate, and that's why we have the concentration proofs. So, and everything I've said so far actually comes with a caveat, is that it's for 0, 1 matrices, and then if you want to generalize to matrices that have real valued entries, for example, the Netflix matrix has values 1 through 5, you have to be careful, and the carefulness shows itself in this form, in that take your non-zeros, scale them all to be between -1 and 1, and then take the smallest non-zero in magnitude, and then the shuffle size is, call that h. And then the shuffle size is actually, you have to divide by h squared in the shuffle size that you expect. So for 0, 1 matrices, that's fine, because h is equal to 1 there. If you have a 0, 1 matrix, if all the entries are between are either 0 or 1, the scaling does nothing because all of them are already in between -1 and 1, and then the smallest magnitude that is non-zero is 1. Okay? Okay, so, and the largest reduced key, that happens very trivially. I mean, the proof for that is a one-liner. It happens because cosine similarities are numbers between 0 and 1, and the normalization factor was gamma. So you can't get more than gamma things being sent to the reducer. So that proof is trivial. So that's why I put it up. Okay? So yes, I mentioned this earlier. The fact that we have an inversely proportional sampling scheme requires these concentration inequalities. And the first one is the one about matrix, is about the singular values. So this is the guarantee. The guarantee is that this is our estimate for A transpose A. DBD. B is the matrix of the Bij's that the slide I put up and said, remember that slide? Those Bij's are being shoved into this matrix big B. And then, so remember the Bij's are estimates for the cosine similarity, multiplying by a matrix D, which holds it's a diagonal matrix. It holds the column magnitudes on a diagonal. Multiplying by that on both sides removes the normalization that cosine similarity does, and therefore this becomes an estimator for A transpose A. And then we take that matrix, find its spectral difference with the true A transpose A, and divide, and we want that to be less than epsilon. Okay, so this theorem, the proof of it, uses a concentration inequality that I haven't seen used much. Latala's theorem, it's worth going into for maybe 2 minutes. Given a matrix that has given a matrix that has centered random variables that are independent as its entries, if you can control the second and fourth moments of those entries, then you can also control the 2 norm of the resulting random matrix. Okay, so here's the theorem. It says that if you have the second central moment and the fourth central moment, then you can use that to bound the expectation of the largest singular value of the resulting random matrix. And that's the core of the proof for the concentration of the singular values in dim sum. To plug our values for dim sum into here, we had to analyze these 2 quantities. The first one is simply the variance of what we're computing, the variance of the estimators for the cosine simulators. That was easy. And then what's not easy is the fourth moment. And so that's a bunch of algebra that is definitely in the paper and not worth your time right now. So the second promise is the promise of the cosine similarities being estimated correctly, but with a lower setting of gamma. And that theorem only uses turn-off bounds that are very, very standard. So this basically says that in relative error, the estimation of the particular entry of A transpose A is exponentially small as long as you set gamma to log n over s. So alpha will be log n over s. Okay. Yeah, so this is yeah, you guys could all do this easily, so I'm not going to go into it. All right? So simply set gamma to log n squared over s, and all pairs of cosine similarities greater than s will be guaranteed correct, or at least close to correct. So the take-home message for the sampling scheme is that it effectively neutralizes parallel distribution. So these very popular columns, such as the Godfathering of, they screw you over in your computation. They produce a lot of shuffle, and they produce a lot of, they overload a particular reducer. This way you screw it back. You undo the problem that is happening when you have some very popular columns, both. Yeah. And so in practice, how is this actually being used in practice? Well, it's actually in production at Twitter in 2 places, and then we've used it for some other things too. So in practice, you don't actually use the theorems too carefully. Okay, you have this knob gamma, and you turn it up until your application works. Okay, so it's nice that you know if you turn up gamma high enough, you're guaranteed to work. But you don't actually have to do that, right? You just take it up high until it works. So also one other caveat is that if you're using A transpose A to compute singular values, there's always this issue of squaring the condition number. So if you have an ill-conditioned matrix to begin with, you probably shouldn't be computing A transpose A to compute singular values. But if you want to compute A transpose A for other things, and the singular value concentration gives you some nice effects, then by all means use it. But be careful. Yeah, so whenever you compute A transpose A, you got to be careful for ill-conditioned matrices. And this is one of them. Okay? So for one of the places that this is in use is on Twitter.com. When you follow somebody, you get suggestions of who you might also want to follow. And so these are similar suggestions, similar accounts to what the account you just followed. There are a lot of ways in which we produce these suggestions. There are a lot of ways to produce suggestions, and then we have some machine learning to rank them. But the actual way to produce them in the first place, one of them is via dim sum. Another place at Twitter that this is being used is for similar advertisers. So we have a matrix of clicks, and then of users, and then advertisers on which they clicked. And then we want to find similar advertisers, same deal there. There's a smaller scale experiment which I have a graph for the rows being users and the columns being words. And we're trying to find similar words there. And in that case, you can see how the error rate goes down as you consider those pairs that are more and more similar. So if you care about pairs that are similar, more 10% similar, then you can expect a relative error of around 10%. And if you're just looking for all pairs of words that are similar, this is probably okay, because you actually care about only highly similar things, highly similar pairs of words or pairs of movies, advertisers, whatever. So it's not a big restriction to be looking at only highly similar columns. And as I promised earlier, this all does generalize to a bunch of different similarity schemes. The Jacquard similarity scheme is a little bit different from the rest, but overlap similarity defined with slightly different denominators all work. And again, these are all require slightly different proofs, slightly different concentration inequalities. Definitely not worth going into here, but it's all in the paper. And of course, you can also use locality sensitive hashing to do all of this. And that's where Jacquard similarity comes in. And actually, those mappers and reducers are quite different from what we showed here. And there's a whole set of other results to see how to do min hash on MapReduce, such that shuffle and reduced key complexity is lowered. And the bulk of those theorems are in the Biscoe paper. And that's it. It's the end of the day, so I won't take you any longer. So consider dim sum if you need to square a matrix, basically. Thanks.